dimensionality for the solutions of the three-dimensional primitive equations. The questions addressed here come basically from turbulence. For example, the exponential decay of the Fourier coefficients for the solution justify the existence in the spectrum of a range where the dissipative where actually a dissipative range where the accumulated kinetic energy is neglectable. We will also see two different ways of defining the finite dimensionality for the solutions of the model. Basically speaking, we will need actually a finite number of degrees of freedom in order to control the long time behavior of the solution. Okay, I will start by introducing the model we are working with, the primitive equations. Then I will show the variational formulation for this problem, and I will recall some existence and regularity results existing for this model, and then I will introduce the definitions for the finite dimensionality of the model and prove it. And in the end, we will see the exponential decay of the power spectrum of the solutions. Okay, so as announced, I start by introducing the model. It's pretty well known. The model is describing the motion of oceans. It's obtained from the fundamental laws of physics using two approximations. We use here the hydrostatic approximation, so we take into account the fact that the ocean is much larger than deeper. So in the conservation of the vertical momentum, there are lots of terms when we are scaling that will disappear, and that's why we obtain the hydrostatic equation from the conservation of the vertical momentum. And the second approximation used here is the Boussinesq approximation, which says that actually in the ocean the density varies little from an average value, so it can be considered as constant, except for the term here in the hydrostatic equation. The equations here are the conservation for the horizontal momentum, the hydrostatic equation, conservation for mass, that's the conservation for the energy, diffusion for diffusivity for the salinity, and that's a state equation giving us a law between temperature, salinity, and density. The notations are classical. V here is the horizontal two-dimensional velocity, W is the vertical velocity, F the Coriolis force, P the pressure, G is the gravitational constant, rho is the density, T the temperature, S the salinity. We have here rho 0, T0, and S0. These are some reference average values. T full, S full, and rho full are the full quantities, and in the equations here, T and S are actually perturbations from the average values. The SV term here, it's a forcing term which is introduced for mathematical generality, but in the physical model it's not existing. Here it's non-zero in general. It's related to the solar heating. Okay, so this is the model. I will place myself from now on in a box, and I will work with periodic boundary conditions. And the functions we are considering will have some symmetry properties. We'll work with the horizontal velocity, which is even in the z direction, in the vertical direction, and temperature, which is odd in the z direction. The classical function spaces for this problem will be denoted by V in what follows. which is the space of periodic H1 functions. The dot there is saying that the functions are zero average over the domain. We have the symmetry properties that we imposed, and some conditions saying that the divergence of the average in the vertical direction of the horizontal velocity is 0. Okay, we have H, which is the corresponding space actually in L2, and V2 is the space with higher regularity. We'll ask actually that the second order derivatives to be in L2. Okay, so that's the classical function spaces we'll work with. Well, we note here that we impose an initial condition just for UV and T, not for all the unknowns we had in the model. That's because the variables are of two types. We distinguish between prognostic variables for this problem, which are UV and T, for which we need an initial condition in order to be able to find the evolution in time, and diagnostic variables, which are W and the pressure P, which these ones can be found at each instant of time from the values of the prognostical variables. The vertical velocity is found by integration in the vertical direction in the conservation of mass equation, and the pressure is found up to the surface pressure by integration also in the vertical direction in the equation for in the hydrostatic equation. I forgot to mention that actually in what follows I drop the salinity equation because from the mathematical point of view it didn't bring any information or difficulty. So that's why we'll have just the temperature in what follows. Okay. The variational formulation of this problem is this one. So we are searching for a solution U that satisfies this problem here. The operators here, A, for example, is coming from the viscosity terms in the equation. E here is coming from the Coriolis force term, and B here it's coming from the nonlinearity of the equation. And we are searching for a solution U that satisfies this equation for all test functions in the space V. The properties that we will use for these forms are that A and E are bilinear continuous. We had here a constant K when we defined the form A. It was chosen conveniently such this form to be coercive on V. We have also properties on the trilinear form, which is continuous on these spaces. We have an orthogonality property saying that if the last two variables are equal, actually the form is 0. From here we have this antisymmetric property in the last two variables, and this is an estimate that I will often use in what follows in order to handle the nonlinear term. Okay, this equation can be also written as an operator equation with A and E related to the forms A and E. This is the coercivity property. This translates the coercivity property, and this translates the orthogonality. Okay, so that's the model we are working with. I will now recall some results on the well-posedness of this model. It's not a complete list of results. The first developments in the study, in the mathematical study of this model, are from the 90s with a series of works by Lyons, Temam, and Wang. where they proved the global existence of weak solutions. For more than a decade, this problem was considered probably as difficult as Navier-Stokes, even not more difficult from the well-posedness point of view, and that's because the nonlinearity of this problem is stronger than in Navier-Stokes. For the strong solutions, at a certain moment, it was thought that there's just a local in time result. I cite here the work of Temam and Ziana. For a special domain, for thin domains, and working with initial data that depend inverse proportionally on the thickness of the domain, Hu, Temam, and Zian proved the global existence of strong solutions. And in 2005, Kao and Titi proved the global existence of strong solutions in arbitrary domains, proving that actually the intuition that this model would be less regular than Navier-Stokes was actually wrong. Here, the depth of the domain is constant, but it's arbitrary. In 2007, Zhu proved the existence of the global attractor for strong solutions. And also in 2007, Kukavica and Zian proved the global existence of strong solutions in a domain with variable bottom and where they considered different boundary conditions from the conditions considered by Kao and Titi previously. For a periodic case, we can prove the global existence in time of very irregular solutions, provided that the initial condition and the forcing terms are regular enough. More than that, we can actually prove the existence of absorbing sets in these spaces. So I cite here this result with an initial condition regular enough and a forcing term that is regular enough will have a unique global solution that is pretty regular. Okay, so that's the model. Now we would like to see ways of parametrizing, of describing this long time behavior of the solution with a finite number of degrees of freedom. We will see two ways of doing this. First of all, we will see that we can determine the behavior, the long time behavior, by using the informations we have on a discrete set of points. That's the case of determining nodes. And we'll see also that we can do that by the determination of the long time behavior of the solution when we project it on a finite space. And that's the case for the determining modes. In the context of Navier-Stokes equations, that's a lot of work on this. The first results are by Foyash and Prodi, where they proved the existence of the determining modes, and then improvements of these results are due to Foyash and Temam, Constantin Foyash, Manley and Temam, Jones and Titi, Doring and Gibbon, Constantin Doring and Titi, and that's again not a complete list of results. Okay, the first notion that I introduce here is the notion of determining nodes. This is coming from real situations. We would like actually to be able to measure what's going on with the solution on a finite number of points in the physical domain, and once we know what's going on there, how the solution is behaving for a long time, then to be able to know what's going on everywhere in the space. Mathematically, this will translate as following. We will suppose that we have two forcing terms that have the same asymptotic behavior. So here the asymptotic behavior is translated by the fact that the norm, the H1 norm of this difference goes to 0 as the time t goes to infinity. We will consider a set of n points uniformly distributed in the domain. We note this set with E, and we suppose that the corresponding two solutions have the same asymptotic behavior at these points, meaning that the maximum of the difference between these solutions at these points goes to 0 as the time t goes to infinity. If we have that the two solutions have the same asymptotic behavior as the time t goes to infinity uniformly in space, then we will say about this set E that it's a set of determining nodes. In order to prove this, I will need two technical results. The first result is saying that once we cover the domain omega with n identical cubes of length L, and we consider a set of n points uniformly distributed in these cubes, we can bound the H2 norm of a function in terms of the maximum of the function of these points, of the length L of the small cubes, and of the H3 norm of the function. The second technical result that I will use is due to Jones and Titi, and says that if a function is satisfying this differential inequality, where alpha and beta are satisfying certain conditions, then we can say that the function is going to 0 as the time t goes to infinity. So actually what we will want to do is to obtain this kind of differential inequality for the difference between the solutions, and to prove that this difference between the solutions goes to 0 in a certain norm as the time t goes to infinity. That's basically how we will use this lemma. In what follows, we will prove even a stronger result than what was asked in the definition for having a set of determining nodes. We will actually prove this asymptotic behavior in a stronger norm, in the H2 norm. Okay, the first thing we will do is to see what is the equation satisfied by the difference between the two solutions. The equation is given here, and then to take a test function which is minus Laplacian squared of u. We will obtain for Laplacian of u, for the Laplacian of the difference between the solutions, this differential inequality, and we will need to bound the terms from the right hand side of this inequality. Now here we will use the bounds for the nonlinear term, and the idea will be actually each time to separate the terms where we have the H3 norm of u with a smaller coefficient to absorb it on the left hand side, and the rest of the terms. So this is actually what is going on here. We separated this quantity, same here and same here, and we'll keep the rest of the terms. For the forcing term, the estimate is pretty easy. We do the same thing. We'll keep we separate this H3 norm of u, and we introduce everything in our differential inequality to obtain this one. In order to be able to apply that generalized Gronal lemma, we would need to have here the same function of that we had here. So we need a Laplacian of u instead of this h-free norm of u. For that, we use the first technical result that we had. So we can bound from below the h-free norm of a function in terms of the Laplacian, in terms of the length of the cubes, and of the maximum of the function at the values of this set. So introducing this lower bound in this differential inequality, we will obtain this one, which now looks like the one from the Gronwall lemma. We have the function psi, which is Laplacian of u. We have a function alpha, and we have a function beta. We need to check the conditions on alpha and beta in order to have the result that this function is going to 0 as the time t goes to infinity. And for beta, the condition is ensured just by the fact that we made certain assumptions on the forcing terms and on the solutions. This will go to 0 as the time t goes to infinity, because we supposed the two forcing terms have the same asymptotic behavior, and this quantity also goes to here because we supposed the corresponding solutions have the same asymptotic behavior in the points of the set we considered. We also need to check the condition on the function alpha, and this can be checked because we know the result on the existence of absorbing sets in all Sobolev spaces, so we can bound from below this quantity. Now all we want is that limit inf here of this average in time to be superior to 0. Well, this will be obtained when L is small enough, so when this quantity here dominates the constant we have here. This shows that if the cubes are small enough, then our set is a set of determining nodes, and that's the condition here we have on the determining nodes. Okay, the second notion that I introduced is the notion of determining modes, which says, roughly speaking, that if we know what's going on with just a finite truncation of the solution, we consider just the first m modes from the Fourier series development of the solution, then we know what's going on with the whole solution. We know the long time behavior of the whole solution. More exactly, we will consider again two forcing terms that have the same asymptotic behavior. We also consider two corresponding solutions for these forcing terms. We write them in terms of the eigenfunctions of the operator A. We take the projection on the first m mode, and we will use the notation Qm for the remaining part of modes. We will say that the first m modes are determining modes if once we know the asymptotic behavior of this first m mode, then we know the asymptotic behavior of the solutions on the whole. Okay. We'll do basically the same thing as before, meaning that we consider the difference between the two solutions. We assume that the projection on the first modes of this difference goes to 0 as the time t goes to infinity, and we write the equation for this difference between the solutions. we want to show that the remaining part of the solution go also to 0. In order to have that, we'll take the scalar product of this equation with Qm of W, with the remaining part. We'll obtain this inequality, and we need to estimate this term from the right hand side. I will not enter in all the details, but we will use again the same kind of estimates for the nonlinearity, for the nonlinear terms, and we will also use these relations between the norm L2 of the projection, the H1 norm of the projection, and the eigenvalues. We have these estimates here and this one also, between the norm L2 and the norm H2. Okay, we introduce all this into our differential inequality, and we obtain this differential inequality. Now, we would like again to use the generalized Gromov lemma. So we would like again, instead of having here this H1 norm, to have the L2 norm of Qm. For that, we will use this relation between the H1 norm, which is bounded from below by the L2 norm of Qm of W, and the square of the m plus 1th eigenvalue, and introducing this inequality into the previous one, we can write it in the form required by the generalized Gromov lemma. So we have this differential inequality with beta, which is this function that goes to 0 because of our initial assumptions, and alpha, which is this function here. So it's given in terms of the H1 norm of the solution and H2 norm of the solution. Okay, now since we know that the solution is very regular and we have uniform bounds in time for the solution, our condition on the alpha function is satisfied once we take lambda n plus 1 big enough in order to be bigger than these bounds we have here. So this is how we can be sure that the first m modes are determining once the eigenvalue satisfies this condition related to the bounds of the solution in H1 and in H2. If a little remark on the determining modes, if instead of using that kind of estimate for the nonlinear term, we would have used something like this, bounding actually in L infinity gradient of the solution. The generalized Gromov inequality would have been modified with an alpha of this form. So by defining a sort of modified mean rate of energy dissipation in this term, we could impose a condition on the first m modes in terms of this mean rate of energy dissipation. So once we have the m plus 1th eigenvalue big enough to be bigger than this quantity, we know that the first m modes are determining. Okay, that was all about the finite dimensionality. Now I will talk a little bit about the exponential decay of the power spectrum of the solutions. This mathematically translates into the study of the regularity of the solution into a certain class of functions called Jeffrey regularity, Jeffrey class of regularity. For the Navier-Stokes equations, the first studies in this direction were done by Foyash and Temama, and the result was improved later by Doering and Titi. We recall here some of the notations. So we work with periodic functions. We have this notation here. And we define the Jeffrey class of functions. There are actually functions for which this quantity here is bounded. So we see that the Fourier coefficients are decaying in an exponential manner. We also use at a certain moment another Jeffrey class of functions. It's the class of functions for which this quantity is bounded. So the Fourier coefficients multiplied by an exponential and some polynomial in K. Okay, these are just some notations. In order to prove the Jeffrey regularity of the solution, we will need to be able to control the nonlinearity of the equation. So we have a technical result on this, which looks like this. I will not enter into the details, but we will use this result in order to bound the nonlinearity. Okay, if we start by trying to show directly into our model that the solution is regular in this Jeffrey space, we will discover that at a certain moment we are obliged to consider small initial data, and that's because actually the nonlinearity is pretty strong and we can't handle it well enough. In order to avoid this constraint on the size of the initial data, we will split the solution into a part which satisfies the linear problem with the initial data u0, and a remaining part which satisfies a nonlinear problem, this time with an initial data 0. Okay, we will estimate first the linear part. So we will obtain estimates on u star. For this we apply this operator to our equation, and then we take the scalar product with this operator here. And by using the coercivity of the form A plus E, we end up with this kind of estimate. Now, this term here can be bounded from below in terms of this term of the norm in V by using the Poincare inequality. And if the coefficient here is small enough, the term from the right-hand side will be absorbed by this one. So we will consider here a tau, which is small enough so that this part here to be absorbed. So we'll have this kind of inequality. Using the Gronwall lemma, we end up with estimates on this linear part of the solution. And this, by using the same arguments, we end up with estimates even more regular for this part of the solution. Now, we will need to do the same thing for the nonlinear part. Here we use the estimate on the nonlinearity that I showed at the beginning. And we will obtain this kind of differential inequality where f and g are functions in terms of u star of the solution of the linear part of the equation, for which we already have estimates. So we control these terms, f and g. We note here that this term here is too strong to be absorbed by the second term from the left-hand side, unless this norm in V is small enough, is smaller than C0 over 2. Since the initial condition we considered for the nonlinear part is 0, we will suppose that on a certain finite interval of time, the term here is indeed small enough, and it can be absorbed from on this one. So instead of 41, we will get this differential inequality with okay, f and g what are given, and we can apply the classical Gronoan lemma in order to obtain a bound on the nonlinear part of the solution in V. Now this estimate here, this inequality holds as long as this one holds. So I will need to estimate the time on which the length of the time interval on which this estimate that we did here holds. Rather rough estimate on this time is given in terms of the initial condition, the H1 norm of the initial condition, and the H2 norm of the initial condition. Okay, so now we have a bound on the linear part of the solution, on the nonlinear part of the solution. We put them together and we obtain this bound on the whole solution. When we translate this in Fourier series, this implies that the Fourier coefficients have an exponential decay, as we can see here. Placing ourselves in T star, we see that we have the exponential decay that is given here by lambda star. But now, since we know that our solution is globally in time bounded uniformly in V and in H2, we can reiterate the argument we did on intervals of time of length T star. So by reiterating this argument, we can actually show that after a transient time T star, we will have this decay of the Fourier spectrum given in terms of the supremum of the H1 norm of the solution and of the supremum of the H2 norm of the solution. Okay, and I think I'll stop here. Thank you. Yeah.
Could you just remark briefly how your results, both in terms of exponential decay and the dimension, compare with Navier-Stokes?
They are worse than for Navier-Stokes.
Well, how much worse?
How much worse? For Navier-Stokes, actually for Navier-Stokes, we never have an H2 bound. We just have this this bound on the supremum of H1 norm.
And about the determining modes?
The same. It's same situation. And here also for the determining modes, this estimate here, it's normally I think for Navier-Stokes it's at it's power 1/3, and here it's the way it is. So 1/4. So.
Let me add a comment on this question, which is a little bit unfair in the following sense. At least this group of practitioners, turbulence group, they gave us some intuition in Navier-Stokes. What do they expect about the number of degrees of freedom in terms of Reynolds number? In the case of primitive equation, nobody come with such an assertion.
Exactly. Yeah.
And therefore, we don't know whatever estimate she gets if it's really what physicists really assert or not. On the other hand, in Navier-Stokes 3D, you don't have enough mathematical tools to prove whatever the physicists are asserting. So if the geophysics community gives some assertion of what's the number of degrees of freedom they expect in the primitive equations, maybe at least there is some guidance of where to head or where to shoot or to sharpen your skills to get into that. So in that sense, I think...
no, I'm just suggesting it's no excuse to write another paper.
At the moment, it is basically, I think what she did here is in some sense just an attempt to get number of degrees of freedom, inspired what we know for 2D.
Yeah.
For two dimensions, there are some close, sharp
Well, it wasn't obtained in one go, right? Like there were several steps to get to the optimal what we have now.
But to add to that, I mean, I think many decades ago, when 2D Navier-Stokes, the first in 2D Navier-Stokes, the first estimate was something like exponential of the Grashof number. Then it came down to g cubed, then g squared, then g to the 2/3, and you always need a first result to start off, basically, and then people can start taking an axe and chopping away at it. There's a question on the back.
Yeah, we're changing subject. This could be very unfriendly, but you said pretty much beginning, you're going to drop salinity because it doesn't make any mathematical difference.
Yeah.
But physically, by dropping salinity, you lose double diffusion. So nature of system should be different.
Yes, but here by keeping the salinity in the model wouldn't have changed anything with respect to the result actually.
Okay, well, as long as your questions are concerned,
Yeah.
diffusion doesn't affect.
Yeah. Yeah, in what concerns, yeah. And actually, I could cheat a little bit by saying also, here I have a linear law between temperature and salinity. I will combine these equations.
What I thought in my mind,
yeah, I'll combine these equations. I will get an equation on...
you will call it future salinity or something.
Yeah, and it's on the density, and I keep it for the density, and actually it's exactly the same as for the temperature.
So long as viscosity is the same for temperature and salinity.
Yeah, yeah. So long as I have, yeah.
And that's one of the most fascinating questions in oceanography, I think. Diffusion rates are so different.
I don't have a proportionality between the coefficients. I can't combine. You say?
Yeah, that's right. That's
Okay.
the case.
Okay.
Well, yeah.
Do we have any more questions, or at least two Givray experts here? Okay, well, thank you very much.
Thank you.